October 29th. This was the date astronomers had anticipated for months. It was the precise moment that the object known as 3I Atlas would make its perihelion, its nearest approach to our Sun. This was a critical flyby, a passage so important that even the smallest variations in its brightness, its flight path, or its heat output could redefine everything we believed we understood about this object. But as the information started to arrive, it was clear that something was amiss. The observed light curve was not aligning with the computer models. The temperature data was contradictory, and the event that many predicted would be a straightforward brightening instead evolved into something profoundly more bizarre. What they saw was an erratic pulse of light, one that seemed to have a rhythm, and it was recorded by 3 separate observatories, all independent of one another. Initially, scientists wrote it off as static, perhaps solar interference, or possibly even a failure in the instruments. But then, irregularities in the timing began to synchronize, matching perfectly down to the minute across completely different systems. The data from the European Space Agency, the Jet Propulsion Laboratory, and multiple amateur sky watchers around the globe all led to an identical conclusion. The perihelion pass had not occurred as predicted. Whatever transpired near the Sun on October 29th, it was not what the scientific models had forecasted. And if this new data is correct, it may demand that we reevaluate not just 3I Atlas, but our entire method for interpreting interstellar objects. The mystery starts with the most fundamental piece of evidence: the way its light fluctuated. In the time frame surrounding its closest approach, dozens of observatories spanning 3 continents were monitoring the luminosity profile of 3I Atlas. This profile is the specific measurement of how its brightness increases and decreases as sunlight bounces off its surface. The predictive models were considered reliable. They had been fine-tuned over many months. Factoring in the object's rotational speed, its reflectivity, or albedo, and its projected size, the light curve was expected to rise to a sharp pinnacle and then gradually diminish as it vanished into the Sun's overwhelming glare. But this is not what the data showed. Instead, the light curve from 3I Atlas revealed a broken, staggered profile. There were 3 distinct peaks, spaced unevenly, and divided by periods of almost complete blackness. The first of these spikes arrived hours before the object even reached perihelion. The second spike occurred at the exact moment of its closest approach. The third, arriving strangely late, materialized after the object should have already been fading. The resulting graph looked less like the flare of a comet and more like a deliberate pulse. Bright, then dark, then bright once more. Each of these surges was logged at intervals of exactly 0.97 hours. When this information arrived at the minor planet center, the analysts there suspected a calibration error. Solar interference is known to cause such effects. It can oversaturate sensors, warp brightness levels, and create false rhythms. But this pattern showed up on instruments located thousands of kilometers from each other. The exact same pulse was recorded in Chile, in Spain, and in Hawaii. Even the solar orbiter, which is stationed millions of kilometers away from Earth, captured it as well. The timing was identical. The amplitude ratio was identical. This was not instrument noise. What made this anomaly even more bizarre was how contained it seemed to be. Typically, when a comet swings around the Sun, its surrounding cloud, or coma, expands in a chaotic way. Bright patches erupt and vanish without any predictable pattern. But the pulse from this object was coherent, as if the very surface reflecting the light was actively modulating it. Some observers noted it as non-random reflectivity. Others labeled it controlled phase oscillation. The mathematics of the event tell a similar tale. At its brightest, 3I Atlas was reflecting 12% more sunlight than its pre-perihelion average. This is a statistically massive leap, given the amount of energy it was receiving. And this change was not a slow buildup. It was practically instantaneous, which suggests that a portion of the object's surface either reoriented itself or its material composition changed in real time. This led to the first major question. Was 3I Atlas spinning in a new way, or was something on its surface moving on its own? When astronomers went back to check its rotational parameters, they discovered small yet significant discrepancies. The object's observable rotational period actually accelerated, shortening by 0.004 hours, roughly 14 seconds, during the perihelion event. That may not sound like much, but for an object moving at almost 100 kilometers per second, it represents a change with a level of precision you would associate with an engineered stabilization system, not a random gravitational pull. A few researchers at the Harvard-Smithsonian Center for Astrophysics observed that this change in rotation lined up perfectly with the peaks in brightness, as if the object's spin was directly connected to the light modulation. Could this indicate that the surface was actively adjusting itself to manage its temperature or its flight path? Skeptics argue for natural causes, like jets of dust or uneven outgassing, which can simulate such effects. But no natural comet in recorded history has ever displayed a triple-peaked reflectivity that was synchronized across multiple instruments. Not even 2I Borisov, the previous confirmed interstellar visitor, showed behavior remotely similar to this. This is the point where the data shifts from intriguing to deeply unsettling. The last peak in brightness, the one that was recorded hours after perihelion, happened when 3I Atlas was already speeding away from the Sun. It was entering a colder region of space where that level of illumination should have been impossible. Instead, the light surged. And it didn't come from the side facing the Sun. It was a glow coming from the shadowed hemisphere, a light from the dark side. That single reading demanded an entirely new analysis. If sunlight wasn't the cause, what was? Thermal inertia, perhaps? Reflection from nearby plasma? Internal luminescence? None of these hypotheses fit the data properly. Some of the data points even revealed a narrow-band spike near 850 nanometers. These are infrared emissions that are more commonly associated with heated metal than with vaporizing ice. By midnight Coordinated Universal Time, the European Space Operations Center flagged the anomaly internally. The memo was short. Possible artificial reflectivity event pending confirmation. It was never intended for the public. In the meantime, amateur astronomers on social media were the first to notice. Sky watchers comparing their exposure frames saw the flicker before any official agency made a statement. Within hours, the theory of a light pulse was spreading faster than the official explanations could be formulated. And yet, nobody could provide a reason why 3 perfectly timed pulses would emanate from an object that was supposedly just tumbling randomly through space. This, however, was just the start. The light curve was only the first sign of something far more profound. Because as soon as the infrared sensors started to measure its temperature, the paradoxes began to stack up. When any object flies close to the Sun, its temperature profile is one of the most straightforward things to calculate. The laws of thermodynamics are not easily broken. Sunlight hits the surface heats up, and it radiates that energy back into space. The resulting curve is smooth, reliable, and entirely predictable. But the curve for 3I Atlas was broken. Infrared measurements from NASA's Parker Solar Probe, the European Space Agency's Solar Orbiter, and several ground-based instruments all captured contradictory thermal patterns during the perihelion window. Instead of a steady rise in temperature as it neared the sun, followed by a plateau at maximum exposure and a gradual cooling, the thermal output of 3I Atlas fluctuated. The heat spiked, then plummeted, then spiked again, all in perfect synchrony with the same time intervals as the light pulses that were recorded earlier. This observation alone was cause for concern. Objects composed of rock and ice do not pulse with heat like a heartbeat. They absorb radiation, and then they release it slowly. But the readings here showed periods where one part of 3I Atlas appeared to be cooling down, while the opposite hemisphere was simultaneously growing hotter, as if the heat was being purposefully redistributed or even managed internally. The instruments on the Parker Solar Probe logged an especially bizarre piece of data. During its perihelion pass, right when the comet should have been soaking up the maximum amount of solar energy, one of its sensors detected a sudden decrease in infrared flux, dropping nearly 20% below the predicted model. The only way to account for such a drop would be if a part of the object's surface was reflecting thermal radiation instead of absorbing it. This implies a surface with high emissivity control, something similar to metallic reflectors or adaptive coatings. Not natural dust, not carbonaceous chondrite, but something else entirely. At the very same time, the solar orbiter detected brief bursts of ultraviolet light around the trailing edge of 3I Atlas. Ultraviolet emissions in that specific wavelength typically signal the presence of ionized metal atoms, not gas or dust. They found nickel, cobalt, and a faint signature of molybdenum. These are all elements that, when vaporized, produce signatures commonly found in industrial alloys subjected to extreme heat. When the spectra were initially processed, the team at the European Space Agency assumed it was contamination from the Sun's own corona. But the chemical ratios were wrong. The Sun does not generate localized nickel lines at that level of intensity. It was as if something on or inside 3I Atlas was shielding, absorbing, or re-emitting solar radiation in a manner that nature seldom permits. To some researchers, this pointed to a hollow or layered structure, an exterior designed to redirect heat to preserve a stable internal equilibrium. To others, it suggested outgassing jets that were ejecting metallic dust. But the real challenge arose when they compared the data from different viewing angles. While the solar orbiter was logging the object's sun-facing side at a reasonable 480 Kelvin for that proximity, the Parker probe's instruments, which were observing the opposite side, registered a temperature almost twice as high for a brief 4-minute period. 960 K. That is hotter than the melting point of many silicates. It's hot enough to turn metal oxides into liquid. And yet, 3I Atlas did not fragment. It didn't shatter. It didn't even flare up. It remained stable. That's when a small internal memo began to pass through the Jet Propulsion Laboratory's heliophysics division. It made mention of thermal phase inversion, a scenario where a body seems to radiate more energy than it is absorbing. This should not be possible without some kind of internal power source or a form of active thermal regulation. That phrase was quietly erased from all subsequent reports. When astronomers using the Subaru telescope in Hawaii reanalyzed the figures, they noticed a subtle detail: the object's thermal lag time. The delay between when it absorbed heat and when it cooled off was too brief. It wasn't hours, it was minutes. A surface that can react that quickly to temperature changes suggests high conductivity, perhaps metallic, perhaps even engineered. Still, the official story remained conservative. They blamed patchy surface activity, uneven jetting, or perhaps a rotating cloud of dust that was reflecting light. Yet, that explanation continued to fail against one inconvenient truth. The heat emissions were directional. The hottest part of the object wasn't even facing the sun. It was offset by approximately 14 degrees, and it was aligned with the very same vector as the asymmetrical plasma jets that were captured moments later. And that brings this story to its next turning point. Because while the heat was already acting abnormally, the material being ejected from 3I Atlas revealed an even more baffling geometry, one that has never been observed in any natural comet jet. With most comets, jets are chaotic. They erupt from weak points on the surface where volatile ices vaporize under the sunlight. They twist, they spread out, and they flicker as the object spins. There is nothing orderly about them. But when astronomers started to examine the high-resolution images from the Solar and Heliospheric Observatory, SOHO, and the ESA's solar orbiter, the pattern coming from 3I Atlas was a different story. Its jets were not just directional, they were predictable. 3 main outflows were logged during the Perihelion event, and each one emerged from nearly identical longitudinal coordinates on the surface. Their vector alignment was so precise that when it was mapped against the object's spin axis, they formed a stable, triangular thrust geometry. This is an orientation that, if it were deliberate, would stabilize the object's motion rather than destabilize it. This geometric stability perplexed the researchers. Comet jets are not supposed to self-correct. They are erratic. Random outgassing is supposed to create torque, which should cause the object to wobble or slow its rotation. But the telemetry data from the European Space Operations Center confirmed that 3I Atlas held a perfectly constant rate of spin throughout the entire event. There was no deceleration, no drift. In fact, after it passed perihelion, its angular momentum actually increased slightly, as if the jets were providing a stabilizing impulse. That kind of sustained equilibrium does not happen by chance. The primary hypothesis from the Max Planck Institute for Solar System Research offered a strange explanation: synchronized outgassing from distributed vents due to internal fracturing. In simpler terms, natural but coordinated pressure points. But others privately observed that the vents appeared to be too evenly spaced, as if they were positioned by design. The solar orbiter's ultraviolet spectrograph captured yet another detail. Each of the 3 jets emitted a slightly different spectral signature. One was high in carbon monoxide, another in molecular oxygen, and the third, the most confusing of all, was a sustained vapor of nickel. That last emission was completely unexpected. Nickel doesn't just vaporize, it demands immense heat, far more than solar radiation could naturally provide at that distance. If those jets were, in fact, rich in nickel, they weren't just venting gas. They were interacting with the plasma in the environment, possibly even using it. NASA's Parker Solar Probe, which was monitoring the local solar wind, recorded micromagnetic fluctuations that coincided with the jet emissions. These were subtle ripples that looked more like controlled bursts than chaotic releases. One scientist termed them coherent plasma interference patterns. Another, more candidly, said, "It looks like thrust." But that concept, propulsion, was rejected almost immediately. Interstellar comets do not maneuver. They are bound by gravity, plain and simple. To suggest that 3I Atlas might be using solar radiation or magnetic fields to control itself would imply it was an active system, something that was designed. Still, the data refused to fit the natural models. When the Hubble Space Telescope was tasked with verifying any changes in its trajectory, the results just added another layer of mystery. Between October 27th and 30th, as the jets fired on and off, the velocity vector of 3I Atlas was altered by 0.2 meters per second. This is a tiny change, but it was detectable. The direction of this drift was a perfect match for the vector predicted if those 3 jets had been acting together as stabilizing thrusters. To put it simply, the object adjusted its own course, just slightly, at the very same moment those jets ignited. Skeptics once again fell back on natural causes: uneven heating, venting, or rotational bias. But no comet observed before, not Borisov, not Oumuamua, had ever demonstrated synchronized ejection patterns from multiple vents that maintained a uniform geometry for hours on end. And this wasn't just about geometry. High-resolution images showed the jets were not messy plumes of dust. They were narrow, columnar outflows, almost beams, that were confined within remarkably tight angles. That level of collimation usually demands magnetic confinement or electrostatic charging, something no natural comet is capable of sustaining. What's more, the jets seemed to be pulsing in unison with the light and thermal oscillations observed earlier. 3 bursts of light, 3 thermal inversions, 3 plasma ejections. The timing was identical. It all suggested a single mechanism, a sequence that was repeating with mechanical precision. And then, the timing discrepancy emerged, deepening the mystery even further. Because while the world was focused on the visual anomalies, the agencies tracking the object started to see small errors creeping into the time data itself. These were errors that should not be possible if every observatory was witnessing the same event at the same time. This was the next anomaly, one that was hidden in the timestamps, where the seconds failed to align and reality itself seemed to be slipping out of sync. Every single observation of the perihelion of 3I Atlas was time-stamped to the millisecond. With 3 major agencies tracking it, NASA, the European Space Agency, and JAXA, synchronization was absolute. Their atomic clocks are constantly cross-referenced through the deep space network. When an object passes its perihelion, the timing can be calculated with such accuracy that even a 1-second difference is seen as a mathematical impossibility. And yet, that is precisely what the data showed. According to the logs at NASA's Jet Propulsion Laboratory, the moment of perihelion, the instant 3I Atlas was at its minimum distance from the Sun, happened at 14:28:36 Coordinated Universal Time. But the ESA's solar orbiter logged the exact same event at 14:31:42 UTC, almost 3 minutes later. JAXA's Hinode probe recorded it even later, at 14:33:09 UTC. At first, analysts assumed it was a lag in the data pipeline, a simple delay in the signal transmission. But the timestamps, which were encoded directly into the raw telemetry, disproved that theory. These were discrepancies in the observation itself, not the network. Each instrument had genuinely recorded the event at a different time. This should be impossible for a single object being tracked simultaneously. Geometry, of course, accounts for light travel time, the tiny delay based on the distance between the instruments. But those corrections are well established and predictable down to the microsecond. What was happening here was something else. The time gap wasn't proportional to the distance. It was fluctuating. The longer an observatory monitored the object, the further its timestamps drifted out of sync with the others. And this pattern was disturbingly consistent with another anomaly: the light pulses. Each timing offset lined up perfectly with one of the brightness surges. If the object was emitting those pulses deliberately, it might have been interfering with how the sensors were detecting its motion. In one internal ESA document, which was later leaked to researchers on an astronomy forum, the language was cautious. Temporal discontinuity coinciding with the phase modulation of luminosity requires further verification. This is scientific understatement for, we have no idea why time isn't lining up. The Japanese team at Hinode suggested a bolder theory: gravitational lensing interference. They proposed that as 3I Atlas passed by the Sun, the local curvature of spacetime was creating micro-delays in the light signal itself. tiny distortions that were magnified by its trajectory. In theory, this could explain an apparent shift in timing. But the math didn't work. For a discrepancy that large, the object would need to have a mass far greater than its estimated size could possibly contain. That paradox led to a second, even more troubling realization. If the timing error wasn't an illusion, then 3I Atlas might have physically been somewhere other than where the instruments thought it was. Telemetry from NASA's Parker Solar Probe hinted at this. While the probe's sensors saw the comet's approach exactly on time, its magnetometer registered field disturbances 200 seconds earlier than expected, as if the object's electromagnetic signature arrived before its visual presence. That is not how natural motion works. A magnetic field cannot travel faster than its source unless what was being measured wasn't purely magnetic. Some theorists suggested plasma reflection, with waves bouncing between the object and the solar corona. Others proposed it was surrounded by a transient energy field. But another, more controversial idea started to gain traction: a temporal phase shift. If 3I Atlas was emitting periodic energy bursts strong enough to interact with the sun's magnetic field, those pulses could be distorting the apparent timing of the signal, like ripples skewing a reflection in water. In that scenario, the object wouldn't be in the wrong place in space, just out of sync in time by a few seconds. But in orbital mechanics, those seconds are critical. A deviation of just 1 second can change a predicted position by thousands of kilometers, which is exactly what happened when scientists recalculated the trajectory of 3I Atlas after perihelion. Its predicted outbound path was no longer matching its observed track. It was off by nearly 4,200 kilometers. On a cosmic scale, that's small, but it was far too large to be an error margin. Something had given it a subtle push. The perihelion timing error wasn't just a data glitch, it was a signature of its motion, a sign that either our measurements or the object itself had been manipulated. By the time this discrepancy was acknowledged publicly, the next part of the puzzle was already emerging, one hidden deep within its light spectrum. Because when scientists analyzed the wavelengths of light coming from 3I Atlas, they discovered something that has no business existing in any natural comet: traces of manufactured chemistry. The initial spectrographic data started arriving just hours after perihelion, gathered from ground-based observatories in Chile, Spain, and South Africa. The objective was straightforward: break down the light scattering off the object's coma to figure out what it was made of. Every element leaves a unique fingerprint, a specific pattern of absorption and emission lines. Using these, scientists can determine if a comet is made of carbon, water, or metals. But when the spectral graphs were analyzed, confusion spread rapidly. The lines they expected to see, hydroxyl, cyanide, carbon monoxide, were present, but they were faint. In their place were new, unknown peaks, gathered in the near-infrared and ultraviolet bands. They didn't match any known combination of natural volatile materials. At first, the data analysts blamed contamination. They thought it must be stray sunlight reflecting off plasma or sensor noise, or an instrument miscalibration caused by the sun's intense glare. But then, separate teams, located hundreds of kilometers apart, confirmed they were getting the exact same readings. The fingerprints were identical, and what those lines suggested was astounding. They found traces of nickel tetracarbonyl, ferrous oxides, and a faint but consistent ratio of chromium and vanadium compounds. These are not typical comet ingredients. In fact, nickel tetracarbonyl is a highly unstable industrial molecule. On Earth, it's known as a byproduct of metal refining, forming when carbon monoxide is exposed to purified nickel at high temperatures. It does not last long in the vacuum of space, much less appear naturally on a frozen interstellar rock. This detection came from 3 different spectrographs: the Very Large Telescope in Chile, the Nordic Optical Telescope in the Canary Islands, and NASA's Infrared Telescope Facility in Hawaii. All 3 of these instruments detected the same molecular structure, with error margins too narrow to be dismissed. It was as if the surface of 3I Atlas contained refined metal alloys that were reacting to the solar radiation. NASA's official statement was diplomatic. They called it possible nickel-carbon bonding under extreme thermal stress. But metallurgists privately pointed out that the ratios they observed, especially the nickel-to-carbon intensity curve, implied a level of precision far beyond random chemistry. Natural processes create gradients, not exact ratios that stay consistent across multiple observations. And yet, that is precisely what 3I Atlas displayed: a steady composition across 3 emission peaks that spanned more than 4 hours. The anomaly grew deeper when ultraviolet data came in from the ESA's solar orbiter. Hidden in the spectral noise was a narrow band near 253.7 nanometers, a wavelength associated with mercury vapor emissions. Mercury, when it's heated, gives off a distinct UV line at that exact frequency. And mercury is not common in comets. It's volatile, it's toxic, and it's rare in interstellar matter. But it is used on Earth in specific high-temperature vapor systems and in experimental propulsion research. That spectral line appeared for only a brief time, then disappeared as the object moved away from the Sun. But it was there long enough to pose an uncomfortable question. Was something on or inside 3I Atlas actively operating during its perihelion? Even more bizarre were the polarization readings. Normally, when sunlight scatters off comet dust, it creates a predictable polarization pattern. But in this case, the pattern was inverted. The reflected light was polarized negatively, a signature that is only seen when light reflects off smooth, metallic surfaces. This effect had been observed once before, with Oumuamua, though it was much weaker. The reading from 3I Atlas was more extreme, consistent with a structured surface, not an irregular, tumbling rock. When this data was reviewed by Harvard's Galileo project, the same group that had studied Oumuamua years before, one researcher allegedly remarked, "It's as if we're looking at engineered material responding to the sun." Of course, no one was permitted to say that in public. The working papers that were passed around research networks used much safer terminology. Non-silicate reflectors, unusual emission ratios, possible catalytic reaction. But even those cautious phrases couldn't obscure the central fact. Something metallic was interacting with solar radiation in a way that suggested active chemistry, not passive sublimation. When the reflectivity models were revised, they only matched the data when a layered structure was assumed. An outer surface composed of refractory metals, with a subsurface layer containing volatile compounds. This kind of hybrid layering does not happen naturally in interstellar debris. It implies a manufactured, or at least a modified, body. But that was just one anomaly. Because while the spectroscopy hinted at artificiality, the brightness data was revealing a second phenomenon. A jump in reflectivity so extreme that it implied a physical change. In other words, something on 3I Atlas had changed its shape. In the hours following perihelion, telescopes around the globe were waiting to see a simple, expected pattern: dimming. A comet that survives the sun's glare begins to lose heat. Its coma collapses, its tail recedes, its glow fades with distance. This is what physics demands. This is what every model confirms. But 3I Atlas did the opposite. In the 12 hours after perihelion, the object's apparent magnitude jumped by nearly 0.8. That's equivalent to a 60% increase in its brightness. This is not a statistical anomaly. This is a new physical state. It became brighter after its maximum exposure to the sun, precisely when it should have been cooling down. This anomaly was first spotted by the Soho Lasco C3 camera, a wide-angle instrument used to monitor the sun's corona. When analysts looked at the images, they saw that as 3I Atlas moved away from the solar limb, its reflected light became sharper and more coherent. It wasn't the fuzzy glow of dust or gas. It was specular. It was mirror-like. That finding triggered an emergency follow-up by the Subaru telescope in Hawaii and the Las Cumbres Observatory Network. Both institutions recorded identical findings. The phase angle of the reflection indicated a sudden increase in its albedo, or reflectivity, from 0.15 to nearly 0.28 in less than 6 hours. That is nearly double the reflectivity of an average comet nucleus. To account for this, something must have physically changed. Either fresh, pristine ice was somehow exposed, which would normally happen before perihelion, not after, or a layer of the surface had shifted its orientation relative to the sun. But the speed of this change and the precision of the angle suggested something else. The data pointed to an organized structure that was rotating into view. When photometric models were run, a strange pattern was found. The light intensity curve was following a repeating beat. Bright, fade, bright again, every 52 minutes. This was almost a perfect match for the pulse interval they had seen before perihelion. It seemed that the same mechanism that had modulated the object's light as it approached the sun was still active, only now it was operating with greater intensity. Theories quickly split into two factions. The conservative explanation was an outgassing mirror effect, that jets of gas had expelled reflective dust in a temporary flat plane, which briefly mimicked a specular surface. But this hypothesis had trouble explaining why the reflectivity stayed stable for several hours, only to abruptly vanish again once the object passed 0.26 astronomical units from the sun. The alternative explanation, the one that few were willing to commit to writing, was that the object's surface had reoriented itself. Not randomly, but deliberately. The light wasn't scattering in all directions. Instead, it formed a narrow cone of reflection, about 15 degrees wide, which was aimed consistently away from the sun. This is the pattern you would expect from a flat or angled surface, not a tumbling piece of rock. When this data was mapped against the outbound trajectory of 3I Atlas, it showed the reflection cone was perfectly aligned with its flight path, as if the surface was adjusting itself to maintain that precise orientation. For a brief period, it was behaving like a solar sail. The intensity of this reflection corresponded to a small but detectable increase in radiation pressure. It registered a faint acceleration of 0.9 meters per second squared. This was enough to change its velocity by about 80 centimeters per second over a 12-hour period. That is minuscule, but it was measurable. And critically, it matched the direction of its motion. It was not random scattering. NASA's Planetary Defense Office flagged it internally as possible anomalous acceleration. This was the same term that had been used to describe Oumuamua's mysterious boost years prior. But in this case, the evidence was stronger. The alignment, the timing, and the spike in brightness all pointed to a single event. Something changed at perihelion and began to interact with solar photons in a new way. Could a natural comet do this? Perhaps if its surface cracked in just the right way to form a flat, highly reflective plate. But a fracture like that would destabilize its rotation. 3I Atlas didn't wobble. Its spin remained remarkably stable, even slightly more controlled than it was before perihelion. To the astrophysicists who were tracking it, this was the most baffling part. The object didn't just survive the sun's heat, it seemed to adapt to it. A group at the University of Helsinki ran radiative dynamic simulations using the observed light curves. Their conclusion was guarded, but chilling. Reflectivity behavior suggests geometric coherence, inconsistent with random fragmentation. In simple terms, it was behaving like something designed to optimize light pressure. And then came the mass anomaly. Because as the light was increasing, the calculations of its density started to contradict the object's observed motion. If the spike in reflectivity meant its effective surface area had doubled, its mass-to-area ratio should have changed. But the gravitational influence of 3I Atlas stayed constant. The numbers were not adding up, unless a significant portion of its mass was hidden. That realization started the next chapter of this mystery. What exactly was inside 3I Atlas? When an interstellar object flies close to the Sun, the combined measurements of its trajectory, its velocity, and its light reflectivity usually allow scientists to deduce its mass with high precision. It's basic orbital mechanics. The more sunlight an object reflects, the less dense it is likely to be. But after Perihelion, 3I Atlas violated those rules completely. Within days of the event, data from SOHO, the solar orbiter, and ground-based tracking stations were all fed into a single model. The mathematics were not complicated. Its observed acceleration from solar radiation pressure indicated a specific area-to-mass ratio. The problem was that when this ratio was applied to its measured velocity, the result defied physics. The model indicated that the mass of 3I Atlas was far, far greater than its visible size should allow. With an estimated length of only 180 meters, its deceleration from the solar wind should have been easy to measure. Instead, it held steady, too steady. To maintain its trajectory under those conditions, it would need to be at least 10 times denser than any known comet nucleus. That would make it denser than solid iron. And yet, its spectral data clearly showed low-density volatile gases and reflective compounds. The two profiles, structural and compositional, could not exist together in nature. Astronomers at JPL reran the calculations, trying to account for possible jets that were counteracting the radiation pressure. The anomaly didn't go away. Even when factoring in outgassing thrust, the mass discrepancy was still there. That is when the conversation began to change. Perhaps the mass wasn't distributed evenly. Perhaps it was concealed. The term hidden mass started to appear in quiet research correspondence. Hollow or layered object, one with a dense core protected beneath a lightweight exterior, could potentially explain both the optical brightness and the inertial stability. If that were the case, the surface of 3I Atlas would be acting as a reflective shell, while the majority of its true mass remained invisible beneath it. This hypothesis aligned with disturbing accuracy to the other anomalies. The regular pulsing intervals of its light curve, the thermal inversion it experienced during perihelion, even the directional jets. All of these could, in theory, be the result of internal regulation, not surface chemistry. A report from the European Space Astronomy Center, marked internal use only, tried to quantify this discrepancy. It determined that the observable gravitational pull from 3I Atlas indicated a total mass of approximately 33 billion tons. To put that in perspective, that is the same mass as a large mountain on Earth, compressed into an object barely 200 meters wide. The only way this could happen naturally is if the body was composed almost entirely of pure nickel or osmium, both of which are highly improbable for an interstellar wanderer. And yet, the nickel line emissions that were recorded near perihelion suddenly made a lot more sense under this assumption. Could the hidden mass just be a solid metallic interior? It's possible. But this created yet another paradox. If the core was really that dense, its rotation period should have slowed down due to the torque it experienced near perihelion. The sun's gravity and solar tides should have had a noticeable effect on it. Instead, its rotation sped up slightly. This is not the behavior of an inert block of metal. It is, however, consistent with active stabilization. One speculative model, which was shared among heliophysics researchers but never published, suggested that the mass anomaly might be caused by a magnetically shielded core. If the internal structure was generating its own electromagnetic field, it could warp how nearby instruments were measuring its inertia. In other words, it would appear heavier than it actually was. But there is another, simpler explanation. Maybe the instruments were not wrong. Maybe the object truly was that massive, and most of it was simply not visible. Infrared backscatter readings taken from the Parker Solar Probe supported this idea. The probe's instruments picked up faint microwave echoes that were lagging milliseconds behind the reflected solar waves. The timing of these echoes suggested they were penetrating through multiple layers of different densities, as if a radar signal was bouncing through an internal structure, not a single, solid object. A layered construction with hollow regions and dense shielding inside. Whatever it was not a uniform chunk of rock and ice. Some proposed it might be a fragmented core that was being held together by an unusually strong, cohesive material. Others suggested a thin, reflective shell that was encapsulating a dense nucleus, much like a containment casing. But if that is true, then something had to be keeping that shell intact against the extreme thermal stress. That mystery only deepened when gravitational modeling revealed another impossible clue. As 3I Atlas moved away from the sun, its deceleration curve began to flatten, as if some external force was resisting the sun's gravitational pull. It was not in a free fall through the solar system. It was managing its own motion. And that realization forced scientists to re-examine the post-perihelion trajectory data, because whatever was inside that object wasn't just heavy, it was active. By October 30th, as the sun's intense glare started to subside, the global tracking network reacquired 3I Atlas. Initially, everything seemed normal. It was located right where the predictive models said it should be. But within a few hours, small deviations started to manifest. When the European Space Operations Center compared its trajectory to NASA's JPL ephemerides, the two datasets no longer matched. The deviation was minor at first, just a few hundred kilometers, but as the hours passed, it continued to widen, and the direction of the error was telling. Instead of slowing down as it should have after perihelion, 3I Atlas appeared to be gaining velocity. It wasn't a dramatic burst of speed, but a sustained, measurable drift. A persistent increase of about 0.12 meters per second squared. That may sound trivial, yet over a period of several hours, it resulted in a positional offset of thousands of kilometers. No natural explanation could account for it. When comets experience acceleration, it's typically from outgassing jets of gas that act like tiny thrusters as sunlight vaporizes the ice. But those forces are chaotic and rotationally destabilizing. In this case, the spin of 3I Atlas remained constant, its orientation was stable, and the acceleration was not random. It was directional, perfectly aligned with its outbound vector, as if it were actively pushing itself away from the sun. That consistency was the real problem. The ESA's solar orbiter recorded a faint but repeating plasma plume trailing behind the object, visible only at specific wavelengths. It pulsed gently, synchronized with the same 52-minute interval seen in its light curve and its reflectivity cycle. The implication was astounding. The very same rhythmic mechanism that was altering its brightness might now be controlling its movement. At the Jet Propulsion Laboratory, analysts rechecked every possible variable: solar wind drag, radiation pressure, instrument calibration. Nothing could explain the discrepancy. When they reran the orbital projection, something unprecedented emerged. 3I Atlas was no longer following a pure Keplerian path. Its orbit had a micro-curvature deviation, a subtle but undeniable departure from the gravitational baseline, as if an additional low-intensity thrust was constantly being applied. This thrust wasn't even constant. It fluctuated. Between 2:00 hours and 8:00 hours, Coordinated Universal Time on October 30th, the acceleration decreased, then increased again, all in a perfect rhythm that matched the object's own rotational period. The effect was almost like propulsion cycles, controlled bursts of motion timed to its rotation. When data from the Parker Solar Probe was added, the pattern became even sharper. As 3I Atlas journeyed through the inner solar wind, its electromagnetic signature was fluctuating in tandem with these velocity changes. The probe detected recurring ripples in the magnetic field, regular, evenly spaced, and each one corresponded to a microburst of speed. It was as if the object was interacting with the solar wind, using it. Scientists at the Caltech Space Radiation Laboratory suggested an exotic theory. 3I Atlas might have a plasma-conductive surface, capable of converting solar radiation and charged particles into directed thrust. In effect, a photonic or magnetoplasma sail. In theory, it would be using the sun's own energy to control its acceleration without needing propellant. That may sound like science fiction, but the mathematics fit the data. The acceleration amplitude was an exact match for what a 180-meter metallic object with high reflectivity could achieve if it were deliberately oriented at a 15-degree deflection from the sun's radiation vector. This was the same angular offset seen during the reflectivity spike. The same angle, the same periodicity, the same rhythm. By late in the day, on October 30th, the discrepancy in its trajectory had surpassed 4,300 kilometers. NASA quietly issued an update to its internal tracking tables, noting an observed drift consistent with sustained low-magnitude radiation-coupled acceleration. They did not call it propulsion, but it was behaving exactly like it. This realization quickly filtered out to independent observers. Amateur astronomers, comparing their post-perihelion coordinates, noticed the deviation as well, confirming it wasn't just an agency data error. When plotted over time, the path was forming a graceful, precise curve, one that no natural outgassing model was able to replicate. Whatever 3I Atlas was doing, it was doing it with intention. And yet, something else occurred in that very same time frame that made the situation even more complex. Because while the trajectory data was hinting at controlled flight, several observatories abruptly lost sight of the object completely. For nearly 2 full hours, it simply ceased to exist, vanishing from all visible and infrared detection. When it reappeared, its brightness, its speed, and its electromagnetic readings had all changed again. That blackout period remains one of the most debated moments in the entire observation record of 3I Atlas. Some dismiss it as a coincidence, others call it the most important silence in modern astronomical history. It started at 9:42 UTC on October the 30th. The Solar Orbiter's imaging system, which had been tracking 3I Atlas non-stop for over 30 hours, captured its last confirmed image, a faint speck moving out of the coronal boundary. The next scheduled image, just 12 minutes later, came up empty. The object was gone. Initially, the disappearance was attributed to a sensor malfunction. Solar interference can easily blind an instrument for minutes, sometimes even hours. But when ESA engineers checked the telemetry, they saw the camera was operating perfectly. The exposure levels were stable. The alignment system was correct. There was simply no object at the expected coordinates. Simultaneously, ground-based telescopes in Spain, Chile, and South Africa all lost visual contact as well. This was not a network outage. Each observatory uses separate data links and independent systems. Yet every single one of them reported the same thing. 3I Atlas had vanished. The blackout continued for 1 hour and 57 minutes. During that time, even NASA's Parker Solar Probe and SOHO's wide-field cameras could not register any trace of it. Not a light echo, not a trail of dust. Nothing. It was as if the object had phased out of optical existence. When it returned to visibility at 11:39 UTC, the readings were different from the pre-blackout conditions. The object was now several thousand kilometers off its previous course. Its velocity was marginally slower, and most confusingly, its brightness had changed its spectrum. Before the gap, the reflected light was dominated by those same metallic wavelengths they had seen since Perihelion. Afterward, the spectral ratio had shifted, becoming a neutral gray. It was subdued, diffused, and less coherent. In other words, whatever surface had been reflecting light like a mirror was now matte. This kind of transformation should not be possible in nature, not in under 2 hours, and not without shattering. Yet high-resolution analysis confirmed there was no debris field. The object was still intact, its rotation stable. So, what transpired during that blackout? The official explanations were evasive. The European Southern Observatory called it temporary visibility loss due to solar background saturation. NASA termed it a data dropout period. Both agencies neglected to mention that all observatories, including those far away from the sun's interference zone, had lost the signal at the exact same time. Behind the scenes, the event sparked a frenzy of encrypted communications between the agencies. Multiple teams tried to reverse engineer the missing data using indirect clues: magnetometer readings, heliospheric plasma measurements, solar wind deflections. Their goal was to find any trace of an interaction that could explain what happened in those 2 hours. What they discovered was subtle, but deeply disturbing. The Parker Solar Probe's magnetometer had recorded a sharp, transient field inversion at 10:27 UTC, right in the middle of the blackout window. For about 3 minutes, the magnetic polarity in the immediate vicinity of the object flipped, and then returned to normal. This phenomenon is not consistent with normal solar activity. It was localized, isolated, and it dissipated too quickly to have come from the corona. The same inversion was faintly visible in the solar orbiter's plasma wave data. It was as if a self-contained electromagnetic field had collapsed, and then restarted. If this analysis is accurate, 3I Atlas may have temporarily shut itself down. Some theorists suggested an internal reorientation, a maneuver, or perhaps a defensive response to the solar stress. Others proposed something even stranger, that the object's external configuration might have changed during that unobserved period. The shift in its reflectivity afterward strongly suggested that whatever surface had been active before was no longer the same. The blackout left a gap, not just in the timeline, but in the entire narrative. It shattered the data continuity that agencies depend on to separate reality from error. Without those 2 hours, no one can definitively say how 3I Atlas changed from a high-albedo, accelerating object into a dimmer, slower, and seemingly stabilized one. And yet, this wasn't the only inconsistency, because as soon as the object reappeared, the agencies began releasing conflicting reports. The numbers didn't match. The timelines were different again. The scientific record itself was beginning to fracture, just like the data it was trying to describe. By October 31st, Every major observatory capable of tracking the object had filed its post-perihelion report. Usually, these reports all converge, at least within acceptable error margins. But this time, the numbers were irreconcilable. NASA's Jet Propulsion Laboratory issued preliminary telemetry that showed 3I Atlas on an outbound hyperbolic trajectory with a velocity of 93.7 kilometers per second, a brightness magnitude of 13.9, and a minor acceleration anomaly of plus 0.00008 meters per second squared. The European Space Agency, however, reported a velocity of 92.1 kilometers per second, a brightness magnitude of 14.6, and no acceleration anomaly at all. In the meantime, JAXA, the Japan Aerospace Exploration Agency, circulated an internal memo that mentioned a possible deceleration phase consistent with rotational jet activity. 3 agencies, 3 incompatible conclusions, from acceleration to none to deceleration, all describing the same 200-meter object during the same 12-hour period. This kind of discrepancy just doesn't happen. Not with the accuracy of modern telemetry, not when atomic clocks are synchronized across the deep space network. Behind the scenes, data analysts started comparing timestamps, file hashes, and exposure metadata. They found something even more bizarre. The raw observation times were misaligned across the agencies by several minutes, even after all light travel corrections had been applied. The exact same frames, identical images of 3I Atlas, had different timestamps in each dataset. It was as if the event itself had occurred in slightly divergent timelines. These discrepancies were not minor. They suggested that someone, or something, had altered the official record. But what would be the motive? At 1920 UTC, the European Space Agency quietly swapped its online dataset with a new version, deleting the previous velocity measurement and labeling it under recalibration. NASA did the same an hour later, releasing a short statement. Post-perihelion data from multiple sources indicate instrument interference from solar proximity. Observations remain under review. There was no mention of the blackout, no mention of the change in reflectivity, and no mention of the time offsets. When independent researchers tried to access the archived telemetry through NASA's Horizons system, they found that several blocks of data were missing entirely. Specifically, the blocks corresponding to 10:00 to 12:00 UTC, the exact window of the 2-hour disappearance. Some of those deleted packets were eventually recovered from third-party archives, including one from the Solar Orbiter's automated relay node. They contained faint but clear electromagnetic oscillations that were not consistent with background solar activity. It was the same kind of structured waveform you would expect from artificial interference or a controlled emission. Within 48 hours, the argument had spread through academic circles. The Harvard-Smithsonian Astrophysical Data Repository, the European Southern Observatory, and Japan's Institute of Space and Astronomical Science all reported conflicting photometric measurements. The same object, measured by different instruments, seemed to have slightly different brightness decay rates, as if there was more than one 3I Atlas, or as if it had a variable reflective geometry that changed depending on the observer's angle. The suggestion that the object's apparent state depended on who was watching it created a rare level of institutional anxiety. Some called it a data alignment issue. Others conceded privately that it looked like signal interference. A small team within the Galileo project performed its own independent analysis. Their summary, which was never formally published but was leaked on astronomy forums, concluded: the available spectral, photometric, and timing data cannot all be reconciled under any known natural or instrumental model. Discrepancies in independent data sets suggest non-random data alteration, possibly field-induced. In plain English, something was actively tampering with the measurements themselves. Then came the final straw. When the ESA released its revised chemical analysis, supposedly correcting for the earlier sensor noise, a new emission line appeared. It was one that had been absent from all the previous data. It was faint, but it was clear. A nickel emission at 341.4 nanometers. This was the same spectral signature that had been dismissed as an error earlier, only this time it was stronger. That reappearance reignited the entire debate and pointed straight back to the composition anomaly they had seen near Perihelion. Nickel isn't rare in space, but its behavior in this case was. Ordinary comets and asteroids have traces of nickel-iron compounds in their cores, leftovers from the formation of stars. When this material is heated, it vaporizes unevenly, which creates broad, smeared spectral lines. What 3I Atlas displayed was the exact opposite: sharp, discrete, and rhythmic emissions that appeared, vanished, and then reappeared with near-perfect timing. The first nickel signature was logged during perihelion, hidden within the infrared and ultraviolet spectra. The second one surfaced in the post-perihelion phase, weaker but still detectable. The third one arrived after it reappeared from the blackout, when its reflectivity spiked again. Only this time it came in short bursts every 52 minutes, perfectly matching its light and thermal modulation cycle. That repetition was the crucial detail. If the nickel signal was random, it would fluctuate based on solar exposure. Instead, it was pulsing like a beacon. It had a stable amplitude and a fixed interval. When researchers at the University of Bern overlaid the timing of these spectral bursts onto the object's velocity drift data, the correlation was greater than 0.96, a near-perfect match. In other words, every single time the nickel emission flared up, the velocity of 3I Atlas changed fractionally. It was as if the nickel wasn't just a component of the object, it was part of a mechanism. Nickel, especially in a carbonyl or vaporized state, behaves strangely under intense heat and magnetic fields. It absorbs energy, releases it as narrow-band radiation, and can act as a catalyst in metallic plasma environments. Some of these very same principles are studied in experimental propulsion research, specifically in the development of magnetoplasma thrusters and thermochemical engines. So, when the nickel lines kept reappearing, perfectly synchronized with changes in its motion, a few physicists began to whisper the unthinkable. 3I Atlas might be generating controlled energy. No one used the word engine, not in any official capacity. But the language in the technical papers began to change. Terms like directed energy redistribution and structured outgassing modulation started to appear. These are euphemisms that, when you strip away the caution, simply mean control. One ESA internal note, flagged for restricted dissemination, summarized the situation bluntly. Nickel-based emissions appear correlated with trajectory stabilization. If verified, mechanism involves active thermal management inconsistent with natural sublimation. In plain English, something on 3I Atlas was deliberately managing its heat, and it was using nickel to do it. When astronomers reanalyzed the raw spectra, they found something even more striking. The nickel emissions were unusually pure. Natural nickel signatures are always mixed with iron and cobalt. But here, the ratio was exactly 100:1, identical to the refined industrial alloys used on Earth for thermal shielding and high-temperature engineering. That ratio was repeated in every single detection, like a fingerprint. To confirm it wasn't just instrument contamination, a cross-check was run using different calibration baselines. The signal remained. The frequency, the amplitude, and the relative strength were all consistent across multiple instruments and multiple hemispheres. the conclusion was impossible to avoid. The nickel wasn't just random material inside a comet. It was uniform, specific, and behaving as if it were part of an engineered composite layer. Then, another discovery advanced the theory. When the solar orbiter's magnetometer readings were plotted alongside the nickel emission peaks, they revealed microspikes in the local magnetic field strength, tiny, symmetrical increases that occurred with each pulse. This meant the nickel wasn't just glowing, it was ionized. Ionized metal vapor, cycling at regular intervals, synchronized with velocity drift. That is propulsion, or at the very least, a controlled electromagnetic phenomenon that is acting like propulsion. At this stage, the internal tone of the scientific discussion changed. The words artifact, object, or comet started to be replaced by body, system, and finally, craft. Quietly, of course, never in public. But the implication was clear. And the nickel wasn't the only evidence. Data from SOHO's LASCO cameras revealed faint, angular shadows stretching out from the object during specific light bursts, as if reflective panels or layered surfaces were briefly catching the sunlight and then retracting. Each of these panels seemed to correspond with a nickel flare. If these structures were directing or focusing energy, it might explain how such emissions could be maintained without the object disintegrating. By late October 31st, a new pattern was confirmed. The outbound path of 3I Atlas wasn't just being accelerated, it was being adjusted. Its course was bending subtly, moving toward the ecliptic plane, the region of orbital stability where most of the planets in our solar system reside. The alignment was exact. It was deliberate. It was as if the object, having passed, Perihelion, had just chosen its new lane. This realization led to what researchers quietly termed the ecliptic hypothesis. That 3I Atlas wasn't just drifting, it was navigating. Because when you follow the nickel trail, you find rhythm, direction, and a pattern. And it isn't pointing outward toward interstellar space. It's pointing toward the inner system. When the first full post-perihelion trajectory maps were published on October 31st, most analysts assumed the figures were just preliminary. The plotted path, a smooth arc cutting across the inner solar system, seemed plausible. But as more data was collected, subtle details started to conflict. Every hour, its position was slightly further off the predicted curve, and always in the same direction, inward, toward the ecliptic plane. At first, the deviation was minuscule, about 0.2 degrees per hour, easily explained away as residual outgassing. But by November 1st, the pattern had stabilized into a clean vector. The object wasn't just departing from the sun, it was leveling itself out with the solar system's orbital disk. This maneuver, if it were natural, defies all known comet dynamics. Interstellar visitors like Oumuamua or Borisov only pass through the ecliptic by random chance, cutting across it at steep angles before they fly back into deep space. Their paths are ballistic and uncorrected. But 3I Atlas was aligning itself. It was matching its inclination, flattening its arc, and adjusting its outbound tilt by roughly 0.7 degrees per day. That isn't drift, that is a correction. When JPL's orbital solution was run again on November 1st, the software flagged an error. Non-gravitational acceleration detected along tangential axis. In simple terms, the object was steering. It was applying a slow, continuous force parallel to its own orbit. The likely source? Those same periodic nickel emissions. Every pulse matched a fractional lateral acceleration, subtle but measurable. The result was a long, graceful turn, a steady migration from a high-inclination interstellar path toward a near solar plane orbit. By the end of October 31st, It had already shifted its position by nearly 6,000 kilometers laterally, enough to alter its long-term trajectory by millions of kilometers. The solar orbiter's plasma instruments recorded electromagnetic interference that peaked at the exact moments of these lateral shifts. The field disturbances were not random. They oscillated at a fixed frequency, roughly 0.019 Hz, which matched the interval between the light pulses and the magnetic spikes detected earlier. Whatever was propelling 3I Atlas, it was operating rhythmically, methodically, as if it were being guided by an internal clock. The ESA's Dynamics Division quietly circulated a restricted brief, known as ATL-12C. The document, later summarized by the Max Planck Institute, stated, "Observed course, adjustment exhibits coherent acceleration phase matching rotational modulation cycle. No natural jet model reproduces both directionality and stability." The translation: every natural explanation had been ruled out. Still, the official public line remained cautious. Agencies described the object's motion as consistent with outgassing anisotropy. But behind closed doors, the discussions had taken on a very different tone. One veteran orbital analyst described the motion as an object seeking equilibrium. If this ecliptic alignment continued, 3I Atlas would settle into a trajectory that would intersect the orbital plane of Earth by mid-December. This was a coincidence that was difficult to dismiss. But there was another layer to this anomaly, one that was more abstract, yet perhaps even more telling. The object's rotational axis appeared to be shifting slightly as it aligned with the ecliptic, precessing in the same direction as its velocity vector. This kind of gyroscopic correction requires torque, not random torque, but a precisely calculated counter-rotation. Some theorized it was a natural resonance with the sun's magnetic field. Others suspected a more deliberate system, a magnetic or photonic control mechanism hidden within the object's core. If that's true, 3I Atlas was not only adjusting its course, it was maintaining its orientation relative to the sun, just as a spacecraft would to optimize its exposure. The deeper the analysts probed, the clearer it became that the object's motion was exhibiting feedback behavior. Every change in the intensity of the solar wind was met with an immediate, proportional correction from the object. That is not passive dynamics. That is a response. And perhaps most unnervingly, this response became more refined over time. Between October 30th and November 1st, the amplitude of its course corrections decreased by half, even as its precision improved. It was as if the object was calibrating itself, learning the local solar environment and adjusting its parameters until its movement stabilized. By then, a few voices within the research community had stopped calling it a comet at all. They had started using another term, the system. No one dared to define what that meant. But if 3I Atlas was truly in control of its own path, if it was, in essence, navigating, then the question wasn't just how, it was why. Because a trajectory implies a destination. And as that realization began to sink in, a quiet anxiety spread through every institution that was still analyzing its data. There was no consensus left. There was only speculation, factions, and doubt. When 3I Atlas was first spotted months ago, it had united the global research community. Every observatory, from Hawaii to Chile, from Japan to Spain, was working towards the same goal: to track, model, and understand the first interstellar object to ever pass this close to the Sun. But after Perihelion, the data ceased to align. And so did the scientists. In early November, the emails were leaked. One message thread from the ESA's Heliophysics Division, marked internal, not for public dissemination, contained one unmistakable sentence. The observed course correction remains inconsistent with passive forces. Further speculation about artificial mechanisms must be avoided until narrative alignment is achieved. Narrative alignment. That phrase spread through research circles like a contagion. NASA's Jet Propulsion Laboratory adopted the most conservative position. 3I Atlas was, officially, still a natural object. Their public update, released on November 2nd, described its motion as a product of complex solar interactions combined with reflective surface geometry. Behind the scenes, however, several JPL scientists were voicing their frustration. Some had already drafted internal memos demonstrating that solar wind pressure could not possibly account for the uniformity of the acceleration vector. Those memos were never included in the public report. Meanwhile, the European Space Agency split into two camps. The first, run by the Orbital Dynamics Office, maintained that the anomaly was nothing more than instrument noise. The second, a smaller, more discreet group working under the Directorate of Science, had begun to treat the data as proof of an active system. Their language shifted, subtly, almost bureaucratically. Periodic modulation consistent with engineered symmetry. Electromagnetic coherence. Directed energy alignment. In a scientific paper, these phrases appear neutral, but to an astrophysicist, they read like code. Then came the press leak. An independent astrophysicist associated with the Galileo project posted a redacted portion of an ESA preliminary report to a restricted forum. It included a single paragraph that would set off weeks of bitter debate. If 3I Atlas's acceleration were due solely to solar radiation pressure, its area-to-mass ratio would imply an ultra-thin reflective membrane no thicker than 0.3 millimeters. Such geometry, combined with observed structural stability, is inconsistent with any known natural body. Within hours, the forum was erased. But the paragraph was already circulating. The professional backlash was severe. NASA officials dismissed it as a misinterpretation. The ESA asserted it was non-final draft material. JAXA refused to comment at all, but the damage was done. The cracks in the consensus had become fault lines. Conferences turned into confrontations. One side, the thermal naturalists, argued that the nickel signatures and rhythmic emissions were exotic, but still natural phenomena. The opposing side, the controlled motionists, insisted the data clearly implied deliberate modulation. In private calls, some researchers compared the silence from the official agencies to the same confusion that had surrounded Oumuamua years ago. The same caution, the same unwillingness to label the unknown. But this time, the evidence was far richer. The behavior was harder to ignore. It was no longer about the object itself. It was about control. Who had the authority to interpret the event? And who was allowed to define what was real? A senior scientist from the European Southern Observatory captured the atmosphere perfectly. We are no longer studying a comet. We are managing a crisis of consensus. Even within academic institutions, internal firewalls were erected. Access to the raw telemetry was suddenly restricted. Some researchers found they were locked out of the very databases they had helped to create. Others received quiet suggestions to stop speculating about non-natural mechanisms. Meanwhile, a few independent teams went in the opposite direction. No longer bound by agency oversight, they started running open analyses, publishing their spectral overlays, light curve harmonics, and plasma modeling online. Their conclusions, while cautious, all repeated a single refrain: the precision is too perfect. The story briefly broke into the mainstream media before it was smothered by official denials. The word artificial was used in a few interviews, only to be scrubbed from the subsequent transcripts. Major news outlets reverted to calling 3I Atlas a highly unusual comet. But among those who had seen the unfiltered data, the mood was no longer one of excitement. It was one of unease. The object's apparent intelligence, its capacity to adapt, to stabilize, and to align, had become undeniable to anyone who was reading between the lines. And yet, no one wanted to be the first to say it out loud. Not after what happened to those who had spoken too boldly about Oumuamua. Careers had been ruined for less. Still, the facts were accumulating, quietly and relentlessly. The spectral anomalies, the rhythmic emissions, the perihelion blackout, the controlled velocity drift, the ecliptic alignment. Every single unexplained piece was pointing toward one conclusion. 3I Atlas was not behaving like a comet. It was behaving with purpose. As the situation calmed, one final report was circulated through private channels. It was unsigned, unattributed, but its authenticity was verified by multiple recipients. It summarized the entire debacle in a single line. Consensus cannot be maintained where observation contradicts narrative. The scientific front had broken. All that was left was a simple, unavoidable question. If this object was not behaving naturally, what were the implications for everything humanity thought it understood about visitors from interstellar space? By early November, the argument was no longer about the data. It was about the meaning. For decades, science has functioned under a single assumption, that anything passing through our solar system is passive. It is debris, fragments, and wanderers from distant stars, all obeying the same laws of motion as everything else. But 3I Atlas destroyed that framework. Every observation since its perihelion pointed to an object that responded to its environment, rather than just enduring it. And if a response implies intention, then something much deeper is happening. In closed-door meetings, the word artifact began to be used quietly among researchers. Not officially, never in print. But it was appearing in encrypted messages, in off-the-record conversations, and in anonymized internal memos. Some scientists fought the term, arguing that artifact implies an origin, and they were not prepared to make that assumption. Others felt the evidence had already forced that conclusion, because when you arrange all the anomalies in a line, the synchronized pulses, the metallic emissions, the post-perihelion acceleration, the ecliptic realignment, they do not describe random chaos. They describe order. They describe a coherent system, not a dying piece of rock, but a machine. That conclusion, unspoken but universally understood, carried an enormous weight. If 3I Atlas is a machine, or even partially artificial, it proves that at least one civilization, somewhere beyond our sun, has built something capable of interstellar travel, something capable of surviving solar proximity, something capable of performing controlled maneuvers inside another star's gravity well. That is not just an astronomical discovery, it is a paradigm shift. But the implications don't stop there. If 3I Atlas was sent, then why here? Why now? And why was it aligning with the ecliptic, the plane of our planets, of our home, instead of just escaping back into deep space as every other interstellar object has done? The probability of this being a coincidence is practically zero. A team at the University of Cambridge tried to calculate the odds of a natural interstellar body achieving such a trajectory purely by chance. The answer was less than 1 in 10 to the power of 9. That is rarer than a supernova, bright enough to be seen with the naked eye occurring twice in the same century. It is very difficult to call that random. Others proposed a different motive. Perhaps it wasn't targeting the ecliptic. Perhaps it was using it. The solar plane provides gravitational and electromagnetic stability. It is the ideal path for observing planetary systems. A natural choice for a probe, not a comet. And yet, as the whispers of artificiality grew, some scientists turned their attention inward, to what this discovery meant for humanity itself. If something built 3I Atlas, and if, as some historical orbit models now suggest, it has been here before, then we may have been observed long before we ever had the technology to see it. Perhaps none of the interstellar visitors were random. Perhaps we simply weren't paying attention. The philosophical shockwave began to rival the scientific one. Astrobiologists issued warnings that confirming an artificial origin could destabilize public trust in science, in religion, and even in geopolitics. Agencies began to review disclosure protocols. Some referenced procedures that were originally drafted for non-terrestrial intelligence contingencies, documents that officially do not exist. Others argued that silence was the only logical response. Without direct proof, a transmission, a pattern, a signal, the story could still be managed under the familiar headline of unexplained natural behavior. But silence only fueled the suspicion. Independent astronomers were already publishing their own analyses. Amateur spectrographs were replicating the nickel emission lines. Citizen analysts were plotting the trajectory drift, confirming the ecliptic alignment. The data was no longer controllable. The question had escaped the laboratories. And right behind it came a more unsettling one. If 3I Atlas was built, what was it built to do? Observation? Exploration? Seeding? Surveillance? No one knows. The object remains too distant, too small, and too quiet. It emits no detectable radio signal, no beacon, no code. Whatever form of communication it might use, if it uses any, operates beyond our current capacity to understand. But absence of evidence is not evidence of absence. And perhaps, as some are quietly suggesting, its purpose was never to communicate. Perhaps it only came to watch. Because the more the data is analyzed, the more deliberate it feels. Measured, precise, patient. A pattern of behavior that isn't seeking attention, but rather endurance. Like a message written not for us, but for whoever comes after us. A sign that the void between the stars is not empty. The implications of this go far beyond astronomy. They strike at the very foundation of human perspective. If we are being watched, then the question is no longer, are we alone? The question is, why now? And if what just passed our sun was not a first-time visitor, but a returning observer, one we failed to recognize until this moment, then perhaps we were never the discoverers in this story at all. Perhaps we were the discovered. For years, astronomers will continue to pick through this data. They will correct the numbers, rewrite the models, and argue over decimal points. They will refine the orbital paths, compare the brightness ratios, and debate whether 3I Atlas was a fragment, a comet, or something else entirely. But beneath every new calculation will be the same unanswered question. Why did it behave as though it was alive? The observations themselves are permanent now. The synchronized pulses, the surge in reflectivity, the nickel vapor trails that align too perfectly with its motion to be random, the disappearance and reappearance timed to its own internal rhythm, the subtle, steady turn toward the ecliptic, as if it were taking up a position. Any one of these events, by itself, could be explained away. A statistical fluke, a measurement error, a trick of the light. But together they form a pattern that is too deliberate to be dismissed. Perhaps 3I Atlas was just nature's most complex illusion, a frozen traveler sculpted by chaos to perfectly mimic design. Or perhaps it was something far older, far more deliberate, operating by physical laws we have not yet begun to understand. What truly matters is what it left in its wake, a record of motion that does not bow to coincidence. Even at this moment, telescopes are tracking it as it drifts back out, its brightness fading into the black. There are no transmissions, no new anomalies, just the steady, indifferent silence of an object that has finished what it came here to do. Maybe it was observation. Maybe it was calibration. Maybe it was nothing at all. But the timing of its arrival lingers, arriving just as humanity is reaching the edge of its own observational power, just when we are finally beginning to scan the void for signs of others. As if it came to remind us that discovery may not be a one-way street. Because if 3I Atlas was controlled, then somewhere, something guided it here, through the interstellar cold, across millions of years, just to skim our star and leave behind no trace, but questions. And if it wasn't controlled, then nature itself is far stranger and far more intelligent than we have ever dared to imagine. The official reports will be finalized soon. The data archives will be sealed. The public statements will be carefully phrased to maintain calm. But the scientists who watched those first irregular pulses, they will remember. Because once you have seen an object behave as though it decided to survive the sun, you cannot unsee it. So 3I Atlas moves on, quiet, distant, and fading. And yet, a part of it stays here, in the empty space it left behind, in the unanswered questions that now orbit its memory. It was not a discovery. It was not contact. But it was the shadow of both. Whatever passed near our sun on October 29th may never be fully explained. But its trajectory, its silence, and its precision have changed something fundamental. Because sometimes, the most profound message isn't in what is said, but in what refuses to be.